All right, thank you, Kyle. Good morning. So I'm just curious, how many people have actually used the solver? Okay, so a few hands. So there are multiple ways to do automation in Synergy, and the solver is Dominion's method of choice just because of its power and the flexibility, configurability. And I checked last night, I think we've been using this for 12 or 13 years. So we've got quite a bit of experience with it. So after a bit of an overview of our organization, I will talk about the electric solver and how that kind of fits into our automation framework. And now talk about one of our most important processes, and that's the model build. And then I'll go over a little bit of some other processes and where we want to go with the solver. So Melissa already showed you these yesterday, but I'm going to be talking primarily about our Virginia and North Carolina electric franchise area. Just a reminder, we have 600 substations and 1,800 feeders. So we've just kind of gone through a reorganization in the past 3 or 4 months with our grid planning team. We have a 3-person team just to work on the model. That includes Melissa, Paul Ireland, which you may have met from previous meetings, and myself. And we primarily build the model and maintain it, and then we also do a lot of development with automation, and we're kind of the first line of support for Synergy training. And we have a system planning group, which includes 6 engineers, and their primary focus is the load growth planning. They're kind of our power users for Synergy now, so they'll be doing a lot of the advanced modeling analytics. And we have 3 regions that have 25 engineers split between those. And they're mostly working on local projects, and they'll also take any projects that system planning scopes, and they'll actually run that, kind of be the interface through our project managers, customers, and operations. So our system planning group is more of a kind of a data-driven approach to planning, where the regional planning is more of a reactive to local problems. So the electric solver, it's a COM-based simulation engine. COM means component object model. Is that right, Larry? It's a very old technology. It's been around forever, but it's still quite relevant for software like Synergy. The solver exposes Synergy modeling, analytic functions, but there's no user interface. So it's kind of like just a programmer's interface to all the Synergy technology. You can kind of think of it like scripting, but it's a little bit more powerful, more detailed. You can get to the solver through things like a Visual Studio application. You've got VB, C#, C++. You can also access it through Python within the Synergy GUI. I've never done that, but apparently that works. And you can also just use Microsoft Office. They've got that Visual Basic for applications, and you can fire off a session of solver that way. So I kind of give you a layout of how the I guess how all of our build process comes together at Dominion. This is kind of typical for most companies, where we do data mining from our GIS system, our CIS, to get customer data that comes in through the CMM module, and then OMS data to get outage events. We have several model build processes, one for just the actual topology, one for the CMM data. That goes into our electric model, which everyone can access through the Synergy electric application. But we also have a set of engineering data that goes into these build processes. And the engineering data includes things like ratings on transformers or set points on LTCs or regulators. That kind of data is what you would not normally include in GIS or an asset management system. It's just purely engineering. We kind of got this idea from Northeast Utilities at one of these conferences. But the engineers access that through a kind of a standalone, a sister application to Synergy Electric called the Distribution Model Interface. And it's really just a BI tool that we have for doing everything with the model. So we have several analyses that run on this engineering data and the electric model together, and that goes into an analysis result set where the engineers can query that data through our DMI application. So it's kind of like a good screening tool for, you know, looking for overloads or reliability problems. So I kind of dig into the model build process itself and how it works. This is a .NET application that sits on an application server. It's a virtual server, and it uses two DLLs, and the main one is this model analyzer, which kind of encapsulates the electric solver. The electric solver is a COM-based program, and we actually kind of convert that to a .NET interface because .NET's a little bit easier programming-wise as far as iterating collections. And the model analyzer we just kind of dominionized the electric solver, but we're still using all the electric solver functionality underneath. So in addition to saving and grabbing Synergy data, we also have parallel data specific to Dominion that we save. We've also got a process control DLL that all of our automation uses. That kind of handles task scheduling. So everything that we do with automation, we schedule it through a task system. And then if Model Builder runs into any problems or finds any anomalies in the data, it can report that out to a central error log. So we always have a full view of where our problems are on the system. So going over some of the key steps in the model build process, the first thing we do is just pull the data into Synergy and just in memory start building the model. Then we run a custom script if one is available. We don't have to have too many of these for our feeders, but occasionally we'll just have to run some custom script to like close a switch to feed some unfed sections. We keep that to a minimum. I think it's like 2% of all of our feeders or something like that. Then we import our engineering data, and then we start applying transformations to the model. So when we put this system in, we got away from just showing in Synergy exactly what is shown in GIS. So we're kind of doing these transformations to make the model a little bit more easier to use for the engineers. And I'll go over some specific examples of that in a minute. The next step is we validate the model. So we actually run a load flow with no customers, and we'll do just a basic fault analysis just to make sure that those are running okay. And if either one of those don't, that goes to the error log, and we know to check it in the morning to kind of figure out what's going on there. And then finally, we save the model to the database. So I'll go over some of the transformations we do. This is a typical, 2-transformer substation, 2 buses with a bus tie, and then we have a transfer bus. So one of the things we do is we automatically orient our transformers. Prior to this, we were kind of relying on GIS data to set that orientation, and it did not always work right. So in the solver, it's kind of a pretty trivial thing to figure out how the orientation should be. Another thing we do is get rid of extra equipment that we're not concerned with for distribution planning. So like in this substation, there were more, these buses were longer with things like station service and voltage transformers hanging off of it. We just remove that from the model automatically. Another thing we do is, a transfer bus is normally not fed. So in GIS, all the ties to that transfer bus are open. Well, when we bring that in, that transfer bus is unfed. So we always, switch some stuff in to feed it. Otherwise, when you save that model, those sections, it's really undefined which subtrans that's associated with. And that's done in a deterministic way, so it does it the same way every time. And let's see, finally on this example, we have a cat bank here that has a inline reactor. And inline reactive devices, there's no specific separate equipment category for that in Synergy, because you can just model that with just a plain conductor. It works fine mathematically. The only problem is it's hard for the users to see. So what we actually do is add some graphical points into that line to make it kind of look like a reactor. So hopefully you can see this. It's a little tiny there, but got some main line here overhead that feeds several underground loops. And these loops have fuses on them. And you can see these little short sections coming off the main line. And those little short sections, it's what our GIS folks call stingers. And the purpose of those is to make the locations of these fuses less ambiguous. Without that, these fuses would be sitting on this mainline node, and it wouldn't be obvious which branch that fuse should be on. And you can see that carefully, if you can, with the colors. When they put these stingers in, sometimes it takes on the characteristics of the main line, and sometimes it takes the characteristics of the lateral. And so what we do is just take those stingers out and kind of clean the model up in that respect. Here's another case where we have a switching cabinet that has 2 vacuum fault interrupters and 2 switches in it. They have to have a lot of nodes in there to remove that ambiguity, and so we're taking a lot of sections out of that. And you can see on the bottom here, our designers really love to do these little hump things to indicate there's no connection. That's against Dominion policy, but they're still out there. I kind of hate them, but so what we do is remove a lot of those graphic points. And so that kind of cleans the model up for us. We don't need to know exactly where those cables are. And you can see also we've removed a node at this little corner here. Any time that we have 2 sections that are exactly alike and don't have any devices on it, we combine those sections together. So that not only has visual effects for the users, but it really reduces the load and save time when they're working with the models. So here's an example where we actually put sections back in. We've got a mainline section with an underground loop here. It's got several transformers, and it's not unusual for our designers to draw these as one continuous section. So when we bring it in, we like to break this up into individual sections so that there's a node at every transformer, and that will allow us to take advantage of the elbows at those underground transformers. So if we've got a cable fault, we can actually use by disconnecting elbows and connecting others, we can restore some of our customers before we actually start doing the repair work. And I don't think that's considered in the Synergy reliability analysis yet, but I was talking to Larry yesterday, and I think it's on the list to include that. Finally, I've got an interesting situation here. So I've got a step-down transformer that goes from 34.5 kV down to 12.5 kV. The odd thing here is it's a bank of 3-phase bank of single-phase transformers. 2 of the phases have a 333 kVA transformer, and A phase has a 500. Sometimes I think our designers just look for things to make it difficult for us. So what we do is we split that out into 2 different transformers on 2 different branches. We do this because in Synergy there's not a way to, on a single bank, to split that out. All right, now I'll go into a couple of examples of how we've used the solver to do some analysis, and these are kind of simplistic examples, but a few years ago we got a question from our reliability folks, where are our unfused laterals? And our first question to them was, what is an unfused lateral? This section here, coming off single phase, if this unprotected part is maybe 2 miles, then that might be unfused. But if it's just going 20 feet across the road to the first fuse, then maybe that's not considered unfused. The other thing is, what is a lateral? And they were telling us, well, that's anywhere you've got line coming off of the main line. But even that's kind of ambiguous. What is your main line? So what we did was defined a lateral as any point, any section that has phasing, number of phases less than the source section. So in this case, we're going from a 3-phase to a single phase. And instead of, in our analysis, actually determining what is unfused or not, our approach was to just grab data on every lateral on the system. And so we collected all these data points, and the idea was that we could push all this data to a spreadsheet and let the reliability folks figure out just from the numbers what is fused and unfused. So we kind of have 3 zones of data. One is what is your protected length and customer count, and then the unprotected length and customer count, those are on the lateral. But then we also have a external zone from the lateral of who would be exposed to a fault on the lateral. So if you had a fault here, all of these customers behind the recloser would be affected. So I've got a simplistic example here with a recloser that has no fuse saving and it's 3-phase tripping. We've got 3 laterals. The first lateral has a lot of customers and it's twice as long as the other 2 laterals. Lateral number 2 and 3 only have a few customers on it. So you can see down in the data here, what we kind of nailed down or drilled down to the most important metrics was the unprotected length kind of multiplied by the number of exposed customers. So if you were to have a fault on lateral 2 or 3, you're exposing a greater amount of customers. So even though lateral 1 is twice as long as the other 2, so more exposure lengthwise, your heaviest exposure, when you multiply these links out to the exposed customer count, lateral number 2 and lateral number 3 rise to the list as ones that need to be fused. In this case, it wouldn't make sense to fuse lateral number 1 because without the fuse saving, we're not getting the reclosing benefits if you were to have a fault on this longer section. This was kind of unintuitive for our field guys, and we had to do a lot of training with it. They would go out and start designing, putting fuses in on lateral 1, 2, and 3, and then come back to us and said, hey, what about lateral number 1? Why aren't you putting a fuse there? So we had to do a lot of training with that. Another thing we did was with our cap banks, due to budget issues and timing constraints, we've kind of we went for a few years where we were letting our cap banks kind of deteriorate. If we had a cap bank where a fuse blew, we weren't going out and necessarily replacing the fuse and getting it back online. And so our folks came to us and said, if we were to go out and do some inspections, which ones should we be looking at? Which ones are the critical ones? So the criteria we used is, if a cap bank goes out, we were looking at its effects on voltage violations, both on number of customers and the length of line. And we were also looking at the effects of losses on the system. And so our approach here was it was kind of a brute force algorithm where we were just running every combination of cap banks in and out. So in this case, we've got 5 banks, so you have 32 possible configurations. And we just analyzed the entire system, 1 feeder at a time, and just put all the results out to a database. We analyzed over 2,000 cap banks, and the analysis ran in about 7 hours. And I would say about 98% of that time was just the network time and loading up the model and then saving the results out. Running through all the combinations was extremely fast with the solver. So some other analysis that we do, one is called feeder estimated loads, and this is kind of something that you can do right now with the EA automation in Synergy, but we've had this around for years. We may consider EA automation as a substitute for this, but this program basically just goes out and calculates loading on the entire system for the peak loads. we also have this, we're also supporting a strategic underground program. This is a multi-year program for Dominion where we are undergrounding specific pieces of the system to, to shorten our restoration events in a major storm. So like take a 5-day hurricane event. We want to knock that down to like a 3-day event, just so we can just by getting rid of some of these, backlot construction where you've got overhead and it's just hard to get to. So what we were doing is targeting pieces of the system that had a lot of outages in a short length, so a lot of events per mile, so we can get a lot of bang for our buck if we go in and underground that. And we're already seeing quite a few benefits from that. And yesterday, Melissa talked a bit about our grid transformation program in Virginia. We are also doing ad hoc analysis to support that, just to kind of give us a starting point for scoping some of our projects. So some of the things that we want to do in the future with the analyzer, one is what we're going to call a feeder analyzer, and it's going to be like similar to that feeder estimated loads, but it'll do time series like the 8760 evaluation. And we also want to use it to categorize our feeders by different data points, like whether it's urban or rural, or how close it is to the coast, or whether it's mountainous. And the idea there is if we can get all these statistics for different categories saved into a database, then our big data analytics people can use that in their regressions to do things like come up with our predictive failure rates for equipment, and eventually start doing a real expected reliability performance for our system, instead of just doing the homogeneous failure rates that Melissa mentioned yesterday. Another thing we want to do is create some reduced models for our analyses. These reduced models wouldn't be really for users, but we can do kind of switching studies a lot faster if we can reduce these down to just switching steps with aggregated loads in between. Every year, our low growth planners are required to do a transformer outage contingency. As Melissa mentioned yesterday, our transformers, we load them up to 100% or even greater. So rarely can we just throw in a bus tie to deal with a transformer outage. So our planners have to actually come up with switching steps to prove that we can kind of recover from that outage, and we do that without the help of any DER currently. And that's about a 2-week process for the planners to get through all of their transformers. And we want to automate that where they can define a switching step in our DMI application, and then every year after that, we'll just evaluate those steps and make sure that they'll still work. And finally, we want to do a system-wide feeder reliability analysis. So what Melissa was showing you yesterday, where we do a before and after with the reliability metrics, we want to do a before on the entire system. So basically, we'll be taking outages at every section and determining, what effect that's going to have on our SAIDI, so we can get a before picture on the entire system. So then we're not relying on that graph that Melissa showed yesterday with expected versus actual. Some things to consider with using Solver. Our implementation of this is kind of complex. We've been building on this for years, but it doesn't need to be complex. Our first shot at this was using an Excel spreadsheet to load up Solver and go through all the feeders listed in that spreadsheet. One thing that helps us is that we are business-owned development, so we do our own coding. We get a lot of support from IT as far as our virtual servers and databases, and they've been great with that, but all the coding is done in-house. We have kind of flexible scheduling, so if we get something that comes along that's low-hanging fruit, we can kind of drop one project and work on the more important one, and then get back to the to the less important one later. And we have a tolerance for downtime. So none of these analytics are being used for operations. So if something goes down, you know, we can handle a couple of hours of users not being able to get into this till we figure out the problem. So we don't have to spend a whole lot of time doing testing like you would for, you know, an operations application. So I think that's all I've got. Any questions? Yeah.
How often do you build your model?
So the question is, how often do we build our models? Anytime someone makes a change in GIS, we get an extract from them. So it's usually by the next day we have rebuilt the model. So that runs overnight. And that's a feeder at a time or a substation at a time. Yes.
So you said you custom made a .NET base.
Yes.
Is that hard to do?
So making the .NET interface, yeah, it's a little difficult because you're basically mirroring all the properties and objects that are in the solver. So it's kind of recreating the wheel in that respect. It was worth the time for us because it does make it easier for some of our engineers to use that DLL to run with it, because we kind of dominionized it. We don't expose a lot of the settings that really don't apply to us. There's a big drawback to doing COM to .NET interface like that. You have to do a lot of boxing and unboxing, and that takes a lot of time. So our implementation of Solver is a lot slower than if you were to use it directly. Yeah. I haven't myself. We had someone in our group that tried it a couple of years ago. I don't know if he got very far with it, but we just haven't played around with that much. We would like to look into what we could do for the users in the GUI with that Python scripting. Yeah. We just haven't had time to play around with that.
So you built your GIS department, you give you the new substation.
Yes.
When you rebuild that and you create that central repository, are those individual substation models, or is it one large section model?
It's just one model, but we're just replacing the individual subtrans or feeders in that model. All right.
Where would you start if you're looking to get into this?
Oh, I missed a slide here. So on the, what tab was it? The support tab in Synergy, there is a button there that has all the stuff for Solver. So they've got a user's guide. If you read that user's guide, it's only a few pages long. It's got a great example of there and using Visual Basic. But that's what I did, and I would say within 2 hours, I had a little application running out of a spreadsheet. They've also got their full object model. It's a PDF, and then a more involved developer's reference to get down into the properties and methods of all their objects. All right, thank you.